Oh my God, I talked so much and none of that you heard because my microphone was muted. Good that you mentioned. Okay, publish. Thank you for mentioning it. It would have been a pain to go all the way and then. Okay, first of all, good afternoon. So today I'm going to just finish up the lectures on OS concepts. So we talked about PCBs. We talked about scheduling, and in one word, the scheduling is basically picking the next PCB from the PCBs that are ready to be executed. Now, where do we store those? We store them in ready queue. Is ready queue the only list that we have in the operating system in the kernel? No, we might have a bunch of them. So the one that we just talked is the PCB, it's the ready queue. So in this example, I'm implementing them by a very simple linked list. In fact, this is so simple that you really rarely see something like this. You want to have a really efficient data structure for your ready queue because you don't want to search over all the possible ready processes to find the one that you have to run next. So usually it's a sorted list of the one that has the highest priority, for example, and it's stored in sophisticated data structures such as red-black queues. But I might have other lists of PCBs. For example, let's say you have two processes that are both waiting for your SSD. They both wanted to read a file. So now both of them are blocked and they're ready. They're waiting for their memory. Or maybe you have a process that is listening or waiting for an incoming packet from the network card. So you might have different lists in your kernel. So we started this discussion about multi-processing or multi-programming. The first requirement was scheduling. Now we talked about scheduling. The next one is protection. We want to make sure that the operating system is isolated from processes and processes are isolated from each other. So that's the main goal. This helps us with reliability, right? If we can prevent the operating system to crash, it helps us with security if we want to keep some data secure, with privacy if we don't want people to see each other's data. It also, in some sense, helps us with fairness when it comes to memory allocation that we'll see. The main method, the main algorithm, the main tool that the operating system has in its arsenal to provide protection is through virtual memory to physical memory address translation. So but we you know, when we're talking about protection, we're talking about protecting memory, we're talking about protecting I/O, we're talking about protecting the processor, and again, going back to what I started, the main tool in our arsenal is address translation. So what we do is we restrict the access of each process to its virtual address space. So each process can generate addresses within their address range in a protected way. So somebody asked me on Piazza if a process or a thread has access to all its address space. So for instance, can a process access anything from 0 to 264? And the answer is no, not really, right? Because not all of this virtual address space is allocated to you. This is your virtual address space, but it has to be allocated to you. That's basically when you get segmentation faults. So segmentation fault happens when your process wants to access somewhere in this range, some address in this range that is not allocated to the process yet. And why does it matter for this to be allocated? It matters because of this translation map. So when a new range of virtual addresses is allocated to you, then that means that the translation for that range of address has also been set up by the operating system for you. For instance, let's say that your current stack is here, and now your stack wants to grow further. So this, if your stack grows beyond what it already now has, you might get segmentation fault or page fault. Then operating system wakes up and says, okay, so this is something that I have to do for this process. It wants to expand its stack, and that's allowed. That's fine. So it probably comes and gives you some. Unfortunately, in this graph, there is no extra space. But let's assume that this was not OS code. Let's assume that this was an empty space. So it could come and say, okay, I'm going to allocate this stack to this process, and I'm going to expand this. So let's say a stack was here, and now I have expanded it. So I now put this translation, I add this translation to this translation map. So next time your process wants to access its stack using its virtual address space, it gets translated to find its data here in physical memory. So from its virtual address space to physical address space. And the way we're getting isolation is that if these mappings, the mapping for process 1 and the mapping for process 2, don't have anything in common, then process 1 cannot touch process 2's data, because at the end of the day, process 2's data is somewhere in physical memory that I don't have access to. I don't even know where my own data is, let alone somebody else's. And whatever address that your process generates, it's going to be in its virtual address space, and it will get translated. So that gives you complete isolation. So let's put this. So just one thing, actually, before I move on. You might actually remember something from ECE 252 about sharing memory or memory sharing for IPC, for inter-process communication. The way it's done is basically by let me clean everything here. The way it's done is by putting some again, unfortunately, this doesn't have enough space for me, so I'm going to cross this over. Let's say this, I want to have it as a shared address or shared memory for both of them. I can map somewhere in the virtual address space to this, and somewhere in the virtual address space of this guy to the same file. And these ranges could be different. Maybe this one is from 0xCF blah blah blah, and maybe this one starts from 0xBCF blah blah blah, right? These are virtual addresses, and then I just map them to the same physical address range. Let's say from 0xD something to 0x I don't know, DF something. Now, when this process 2 accesses this virtual address, it's working with data here. when process 1 access this address, it's working with the data here. And because both of them are mapped to the same physical address, they're sharing memory, right? That's how memory sharing for IPC happens. That's one example, for instance, to help you, grasp the idea here. Okay, I got a question here. Can the user change the physical address space setting? Allocated the space? No, the user has no access to physical memory. Physical memory allocation, sorry. In at least in general purpose operating systems. In some operating systems, usually embedded and real-time operating systems, we allow users to work with physical memory. For instance, in RTX that you are implementing, that's the case. So users of your system have full access to physical memory, so they can do whatever they want. But general purpose operating systems, usually the ones that implement virtual memory, then the process has no idea about the physical memory. Okay, let's put this all together. So this is a representation of a Unix process. It has its memory. In particular, in the memory, we're interested in the stack, so I put a stack there. It has its I/O state, whatever files and sockets it has. It has a CPU state, which would be the program counter, the stack pointer, the registers, and all. And then it has a code, a bunch of instructions to be executed. Now, if you run this on a single processor, so in this figure, I have a single processor. There is an operating system, and in this case, I have one thread per process. So this actually indeed was the case for a while in Unix systems. So most of the machines had one single processor, and each process had one thread. So in this case, each process gets to run on the CPU at a time. So they're time sharing the CPU. If you look at the context switching overhead, it's high. If you context switch from process 1 to process 2, you basically need to set up or change the memory. For instance, you probably remember if you have swapped out a process, now you have to bring it back, and that is, generally speaking, very expensive. The other things that are expensive that we will talk about in more details is setting up the page tables, for example, for a new process. So these are really heavy when it comes to overheads and costs. Creating a new process is also costly. Protection is kind of given by default, right? Because the operating system is providing protection by isolating the processes. So you have protection of CPU and protection of your memory and I/O, and that's fine. Sharing, if you want to have sharing between your processes, it's going to be with high overhead, because no matter what kind of IPC you choose, is it time sharing or file sharing or message passing, in all three cases, the operating system is going to be involved, and involvement of operating system means high costs. The next model that we talked about is when you have multiple threads per process. So again, consider a single CPU setting. Now, the context switching overhead decreases in this case, because you might be context switching between threads, and context switching between threads, generally speaking, is not, it doesn't have high overhead because they share data. You don't need to, copy somebody's memory, or you don't need to copy somebody's, I/O stats, because it's already there. If the previous thread that you ran was a thread from your own process, and now you're running a thread within this process, you can reuse the memory stat, the IO stat, because they share, right? So if you are context switching from thread 1 in process 1 to thread 1 in process 2, then you will have to pay the cost of full context switching, meaning that copying the memory and IO stat and all, and that would be expensive. So the reason this cost is annotated as medium is because sometimes you're doing between threads, sometimes you're doing across different processes, and overall you can say the cost is less than what it was before, but it's still sometimes high because you might be context switching between different threads. Now, thread creation the cost is medium compared to process creation. Like if you want to create a process with fork, you sometimes end up copy pasting the entire memory, and that's costly. Whereas if you create a new thread, again, because threads share the address space, you don't need to create a new copy of the process, right? It's already there. You just create a TCB. Now, when it comes to protection, you get CPU protection. One CPU at a time, one thread at a time is running on CPU, and we're keeping track of registers and all. But when it comes to memory I/O, the protection is kind of no, because between the threads, as we discussed in the previous lecture, the operating system doesn't provide any protection. So each thread is capable of messing up the entire address space for other threads, and operating system is not going to meddle in that business. Now, what about sharing overhead? Sharing overhead is considerably low because now you can share data between threads. So you don't need to go through IPC, interprocess communication. You can just, threads can read and write from same variables in the same heap or whatever. So the operating system doesn't need to be involved when we do IPC because all threads have access to the same memory address space. To advance this a little bit, you can add more CPUs. This is what we discussed in the first lecture when we started having systems with more than one CPU. Now, the context switching overhead is considerably lower than the two cases before. The reason is because you have more CPUs, you're going to context switch less, and there is a possibility for you to, let's say, map all the threads for one process to one CPU. So whenever you context switch between them in that CPU, it's always between the same threads from the same process. I mean, of course, it's not always possible, but it is possible. So because we're not context switching much between processes, so the cost has gone down. Thread creation is again, because of what I just said, is lower cost compared to what we had before, because if you map these processes to different cores, then they can easily create processes, create threads. Protection hasn't changed. The CPU is protected, memory is not between the threads, and sharing overhead is low. Yeah, so that's that. Now, somebody asked about hyperthreading before, and I promised to talk about it. Here it comes. Now, I want to advance this model here, where we had a bunch of CPUs, one step further. But to do that, I need some introduction. So let's talk about hyperthreading. Now, to talk about hyperthreading, I need some introduction. So let's say I have a code, and my code is like, load some address X to register 1, and then load, I don't even know if this notation that I'm writing is valid, but whatever, you get the idea, some other address to second register 2, and then add R1 and R2 and write the result in R3. So let's say this is the code that I want to execute. Now, I can start with the first instruction. So I execute this instruction. This is going to go to memory, and going to memory is time consuming. So I'm going to wait a little bit for this to finish. Then I'm going to go to the second one, and I'm going to wait for a little bit to finish. Now, when I say wait a little bit, it means that CPU cycles are going to just come and go without me executing any instruction. So those CPU cycles are just wasted because I couldn't do anything else. I'm waiting for my data to come. And I can't execute this add until R1 and R2 are there, so I have to wait for those. So I'm going to wait for those to finish, then I will do my add. So because of the dependencies between my instructions, I have to wait, right? Okay, so with that in mind, let's look at this. So in a superscalar architecture, now I'm talking about mostly hardware, right? So in this picture that I have, horizontally, I'm looking at time. Sorry, vertically, I'm looking at time. And horizontally, I'm looking at the processing units in my CPU. So basically, if you wish, like if you remember that picture we had before, the ALU, that is what is responsible for doing computation and arithmetic. Let's assume that I put a bunch of ALUs in my machine. So it doesn't only have one ALU. So I might be able to do a bunch of adds at the same time. I don't necessarily am limited to one add per cycle. If I have a bunch of ALUs, then I can do 3 adds. Let's say I have 3 multiplication units in my CPU. So the number of these columns here shows you how many instructions your CPU is capable of executing at any given time. And this depends on how capable your CPU is. This is called superscalar, compared to the one that you have only one computational unit, so you can only execute one instruction per cycle, right? So let's say in this figure, I have a CPU that can execute 3 instructions every cycle because it's powerful. It has multiple computational units. I still have these white cells here. These are the cells that I'm wasting because I can't proceed because there is dependency. You know, let's say I have these 3 instructions here, right? And let's say my CPU is capable of doing 3 instructions per second. Can I do these 3? No, because the third one depends on these 2. So I can't execute the third one unless I have already executed the first 2. So even though if I have 3 computational units, I can potentially and technically do 3 instructions. I can't because these instructions are dependent. So that's why you see these white cells. These are the cells that we're just wasting because we don't have any instruction to execute. We have to wait for the ones that we have already executed, right? Okay, now, so this is how it looks. So let's take a step further. Let's extend this architecture. Let's talk about multiprocessor. What if I have, you know, a processor that has 2 CPUs and each CPU is a superscalar? Okay, good. Now I can run 2 threads. So I can run my thread 1 on CPU 1 with 3 lanes, and I can run thread 2 on CPU 2 with 3 lanes. Now, the same happens, right? Now, there are dependencies for the instructions of thread 2, so I'm still going to see these white cells here. These white cells still exist. Now, take a step further. Let's context switch between these, not context switch. Let's switch between these 2 threads. We're talking about hardware. I'm not talking about the operating system. Hardware can just switch between threads. What do I mean? So the hardware can say, in this cycle, I'm going to run instructions from thread 1. Now, as you can see here, there were these 3 blocks here, I had to wait for the next instructions to execute. Instead of waiting, I execute instructions from thread 2. And then I go back, I execute instructions from thread 1, and then next cycle, I execute instructions from thread 2. Now, for this to happen, of course, the processor, the hardware, has to have more resources to be able to fetch instructions from 2 threads, to be able to have 2 PCs, 2 processor counter, program counter, sorry, 2 stack pointers, 2 everything, right? We need 2 sets of registers because each one of these need their own registers and stuff. So that's one thing that you can do. But as you can see, you'll still have these empty slots here. Even in this fine grain multi-threading, you have these. The last one that kind of nails it is simultaneous multi-threading, or what is called or known as hyperthreading. So this is another step. So let's compare these two. Let's compare fine-grained multi-threading and simultaneous multi-threading. In fine-grained multi-threading, at any given cycle, only one thread has access to all the CPU resources. Now, this is kind of wasteful because what if my thread cannot execute? Let's look at this case. My thread cannot execute 3 instructions. So why should I be given access to all the resources? Now, in this one, however, at any given cycle, both of the threads, let's say, in most of the cases that you have hyperthreading, it's 2. So in this case, both of the threads have access to all the resources. So hardware is going to simultaneously fetch instructions from thread 1 and from thread 2 at the same time. And it's up to hardware how to allocate resources or hardware resources. Maybe both of the threads can execute 2 instructions or 3 instructions. Which one is going to get the resources will depend on how hardware has implemented hyperthreading, which is an area of research by itself. But anyhow, so this is what we mean by hyperthreading. Now, this gives you the least number of these empty cells. We're just really squeezing the resources out of the CPU. Like, we're using all the resources that are available to us by doing this. Now, this is presented to the operating system as 2 separate cores. So if you have a machine and your machine has actually 4 physical CPUs, but each one of them is capable of doing simultaneous multi-threading for 2 threads, then from the operating system's point of view, this machine has 8 CPUs. So operating system can run 8 threads or can schedule 8 threads at any given time. In reality, though, if you have 8 separate CPUs, you get better performance than getting 8 virtual CPUs. Basically, 8 hyper-threaded CPUs. The performance is lower because, as you can see, there is competition for resources, right? In this case, I have, let's say, 3 lanes, and if both of the threads have instructions to execute, I have to choose between them, right? Whereas if I was running them on 2 CPUs, right, there was no competition. Each one of them would get their own resources. Now they're sharing resources. So the advantage of this is I am using less resources and I'm getting higher utilization. In this one, I'm using a lot of resources and my utilization is low. So it's a trade-off between performance and utilization. So hopefully that, if you're interested in knowing more, click on this link, and there are a ton of more information you can get. This is where I'm going to actually end, and I'm not going to go to details of hyperthreading and such. If you take a grad course on computer architecture, you probably will see more on this. So with that, now let's assume that we go back to 4 CPUs, but each one of them is hyper-threaded, so each one of them can run 2 different threads at the same time. Now, this is really good because the context switching overhead is super low, because now I have more CPU units to do my job. But the only downside is this contention that I have created for threads that are running, which I explained. Okay, now we're done with the third OS concept. The fourth OS concept is dual mode operation. Now, for those of you who have watched or attended the tutorial, I went through some of the slides here, so I'm not going to be as deep or as detailed as I did in the tutorial. If you want, you can go and watch the video from the tutorial. I'm going to just quickly recall what I mentioned in the tutorial session last week, I think. Yeah, it was last week. And then we hopefully get to cover more stuff. Okay, so we talked about the fact that in order for you to implement kernel, you want your kernel code to be able to execute some instructions that user code cannot. And to make this distinction, you need the hardware to at least provide 2 modes of operation. In kernel mode, the kernel code runs and it can do whatever it wants. So there is no restriction on what the software can do when the mode of operation is kernel mode. So basically, any instruction that ISA provides can be executed. Now, this is good for the operating system, but we don't want to give this much access to the user. So we at least need another mode of operation. We call it user mode, which is a restricted mode of execution. So some instructions then become unavailable to the user code. For instance, the user code cannot disable interrupts. Or for example, the user code cannot, set change the content of physical memory directly. So, for example, I mean, what I mean is setting up page tables or setting up, interrupt vector table, something like that. So some instructions become unavailable to the code that is running in the user mode. So to this, basically the hardware could provide, if it is just 2 modes, then a single bit, we set it to 1 and 0 to basically switch between these 2 modes. When we transition from user mode to kernel mode, or from kernel mode to user mode, we need to do this in a safe manner. So first, let's discuss how we transfer from user mode to kernel mode. What are the triggers that happen for this transfer? As I mentioned, there are 3. There is the system call. So whenever your user code runs, let's say open, close, read, lsic, open a socket. So these are the system calls. So we trap to the operating system and we start running operating system code. So this is the first one where, you transfer mode from user mode to kernel mode. The second is processor exception. So if your code causes exceptions, like let's say if you divide by 0, or let's say if you access some memory that is not allocated to you and you get a segmentation fault, we're going to transfer the mode. We're going to go from user mode to kernel mode and let the kernel take care of that. The third one is interrupts. So when interrupts happen, let's say the timer interrupt goes off, or let's say a file that you wanted is now ready in memory. So your SSD has transferred data to memory and the data is ready. SSD will raise an exception and interrupts the execution. When that interrupt happens, we go from user mode to kernel mode. We need to implement this transfer in a safe manner. And for that, we have 3 requirements. The first one is we need limited entry points. We should not allow user to jump to wherever it wants into kernel code. So we need to have well-defined entry points to the kernel. The second is atomic change to processor state. So we were running kernel, if we were running user code, PC was pointing to user code. SP, a stack pointer, was pointing to the user stack, and registers contained the results of the code that was executing. Now, if we want to transfer to kernel mode and start running kernel code, it's not just that one bit that has to flip from 0 to 1. We also need to change the PC to now point to kernel code. We also want to change a stack pointer to point to stack, kernel stack. And this is basically the atomic change that we want to happen. We want this to happen atomically. We want the PC to change, SP to change, for example, and the mode to change. So that's another thing. Then the third requirement is we want this whole thing to be transparent to the threads and user processes. What do we mean by that? We mean that they should not notice, right? Nobody should write their code thinking about what happens if I get interrupted at this instruction. What happens if I get interrupted at this line? We don't really care, right? Because it's transparent to us. We wouldn't notice. It's kind of, we get freezed, the operating system goes and does whatever it wants to do, and then comes back and starts executing us again. So somebody has asked, the phrase change atomically sounds ambiguous. What is atomic? So atomic, I mean by atomic at the same time. So I don't want one of the operations happen and the other ones don't happen. I don't want the mode to be flipped, but PC is still pointing to what it was pointing to, right? I want them all to happen or none of them to happen. So that's basically what we mean by atomic. So either we transfer mode, and that means we do a bunch of things together. We change the mode, we change the PC, for example, we save the state, or none of them should happen. There shouldn't be something in between where PC has changed, but then the mode has not changed, or the mode has changed, but PC hasn't changed. We don't want that, right? We want all of them to happen or none of them to happen. So that's what we mean by atomic. Okay, so we talked about the entry point that we said we need a safe entry point. This entry point is interrupt vector table. So what is exactly interrupt vector table? So this is somewhere in the memory, and it's architecture dependent. So in ARM, it's somewhere. In x86, it's somewhere else. So each architecture has its own address for this interrupt vector. Now, this is known to the operating system. So operating system should know for this architecture. Okay, so makes sense. Thank you. Okay, so the operating system that is written for ARM knows where the interrupt vector table in ARM is. The operating system for x86 knows where interrupt table for x86 is, and so on and so forth. Now, operating system goes and sets the entries of the interrupt table. So if an interrupt happens, or if a system call happens, or if an exception happens, hardware by default comes and checks one of the elements of interrupt vector table. So this is hard-coded in the hardware. Hardware knows that if it executes divide by 0, it has to come and check this location. It knows that if the timer interrupt goes off, it has to come and check this location. It knows if it executes a trap for system call, it has to come and check this location. And operating system knows too. Operating system knows that the hardware is going to come and look for what to do here. So I better tell hardware what to do. So operating system comes and basically puts correct values in each of these elements. It says, okay, I know that when interrupt happen, hardware is going to come and check this, so I better write the address of my system call handler in this address, in this element, in this entity. Operating system writes the address of divide by 0 handler in this address, and so on and so forth. So now hardware, if divide by 0 happens, it comes here, and operating system at boot time has put the address of divide by 0 handler there. So hardware comes there, fetches that address, and then jumps to that address. So it's kind of like a collaborative task between hardware and operating system to handle these. And as I mentioned in x86, the convention is that, or the standard is that the first 32 elements are designated for different types of processor exceptions, like divide by 0, like segmentation fault, and so on and so forth. The rest of them, except one, are used for interrupt handling, and one of them, number 60, the 65th element, which has the vector number of 64 because it starts from 0, is used for system call handler. In ARM, the 8th element is for system call handler. So, the address 8, which is if each element has 4 bytes, then it's the 3rd element is used for interrupt for system call handling. So again, this is like architecture dependent. Okay. Now, we discussed this, that if we want to have this transparent mode switch, we want to save the context of the running thread that was interrupted or called system call or had an exception. We want to save its state. Now, where should we save this state? Can we use users' memory for this? And the answer was no, never, ever do that, because it's not safe and it's not secure. We discussed this. So we said that the kernel will have its own stack to save the user data. And we said that some kernels take a step further and allocate a single kernel stack per thread. So not only they have kernel threads, a kernel stack, they have one kernel stack per user thread. So if I'm running thread 1 and thread 1 gets interrupted, I use thread 1's kernel stack to take care of that interrupt. If I was running thread 250 and I got and it called system call, I'm going to use thread 250's stack, kernel stack, to run the system call. And then we ran this example where I'm going to just jump. So the idea was when you're running, as long as you're running your user code, you're going to be using your user stack. The moment you call a system call or an interrupt or an exception happens, we switch to kernel stack and we start using kernel stack. And the first thing that we use it for is to take a copy of the CPU state. And then we will use that kernel stack for whatever code we're going to run. If we're going to run and call system call handler, then we push whatever is related to that handler. For instance, if it is like an open, we want to push the address of the file that we want to open. We want to push, let's say, whatever information is provided to us that is needed to handle this system call. We push them on the kernel stack. And as we will discuss, we need to also check that everything makes sense and there is no, malicious or maliciously put inputs. And then, maybe at some point we're going to call the driver and so on and so forth. Then once we return from those, we pop them and eventually we're ready to just go back. So right before going back, when the thread is now ready, so at this stage, right, the thread is kind of like not ready because we're still handling the system call. Once we're done, we're now ready to go back and execute our thread. Okay. Now, can you disable interrupts in user mode? The answer is no, but in kernel mode you can disable interrupts. In fact, when an interrupt happens and we want to do interrupt handling, the hardware usually automatically disables interrupts. This is usually, it's not all the time, always. You could potentially not disable, but if you don't disable and you're in interrupt handler and another interrupt happens, you run the risk of, having these interrupts within interrupts within interrupts, and it's kind of like a recursive call, and you might end up overflowing your kernel stack, right? Because each interrupt is pushing on the previous one, and you could potentially overflow the kernel stack. And you remember that the kernel stack was limited, like 8 kilobytes. So disabling interrupt is kind of like a simple thing that usually is done. So whenever we come to interrupt handler, we disable the interrupt so that we don't get interrupted again. Some hardware architectures, like if I'm not mistaken, x86 does this automatically. So when it gets interrupted, the hardware disables interrupt by default. Now, if the operating system wants to then enable it, it can enable it if it wants to. But that's something to know and to note. When interrupts are disabled, they don't get ignored, they just get buffered. So while the interrupts are disabled, we kind of track them where they are, how many of them we have. But at the end of the day, hardware has a limited buffers, so it can't buffer interrupts forever. So you usually want to disable interrupts for a short amount of time. If you keep the interrupts disabled, then you might lose the interrupts that are important to you. So that's another thing to keep in mind. These are the instructions to disable and enable interrupts in x86. And they're obviously different in different architectures. So I keep telling you that interrupts cannot be disabled, right? And you might ask, okay, why? Sorry, user programs shouldn't be able to disable interrupts. You might ask why. So I'm answering sort of this question. Let's assume that I have this user thread or user process. It's kind of like an int main. It has a while loop. While true, do nothing. So let's say this is my program. And let's say I have only one CPU, right? If I context switch to this thread and start executing it, if this thread can disable interrupts, it could disable interrupts here. And then go to this while loop. Now, in this while loop, it's not calling any system call. It's not doing any, divide by 0 or any, access to memory. So there would be no exceptions. There is no exception and no system call. And if this thread is able to disable interrupts, then there is no interrupts. So we're screwed. So this process can run forever. How are we going to get the control back? So the way we deal with these situations is that we don't let them disable interrupts. And right before we jump to them, the operating system could set up a timer. So timer is basically a register somewhere in the hardware that you can set a starting address for it. Starting value. And then it counts down every cycle or every 2 cycles or every other cycle, whatever. You can set those information, how frequently you want your timer to decrement. And whenever it gets to 0, you can tell the timer to raise an interrupt. So when it gets to 0, it raises an interrupt. And when an interrupt happens, the hardware automatically gives control back to the kernel, and now kernel can decide what to do. Do I want to continue running this thread, or do I want to context switch to someone else, and so on and so forth. So that's pretty much why we don't want to allow user programs to don't disable interrupts, because if they can, they could take control of the CPU, and then we're just stuck with them forever. Okay, so before I continue, I have a bunch of questions. So in ECE 222, we were taught ISRs have orders of execution. Higher order can interrupt lower order. Okay, right. So I only talked about 2 modes of operation, right? So you might actually have more than 2. And then if you have more than 2, then they can have those hierarchies of higher order ISRs and so on and so forth, right? To have different. Oh, sorry, I'm so sorry. I'm misreading your question. You're talking about the interrupts, right? So you could, right? I think that's you could disable interrupts altogether so that you don't get interrupted, or you could disable them partially, or you could not disable them at all, right? So that's something to keep in mind. I'm talking here about disabling all the interrupts. Now, within interrupts, you have interrupt numbers, and you have priorities over interrupts. So if you get 2 interrupts at the same time, the hardware might prioritize one interrupt over another. and say I'm going to take care of this interrupt with the lower interrupt number. So that's kind of like, I think, what you are referring to, higher order ISRs and lower order ISRs. So it's kind of like hardware sorting the interrupts that you've got based on their numbers, and then going over the higher order interrupts first, and then you can get the lower order interrupts. So sorry, initially I thought you were talking about modes of operation, but I was wrong. So I hope I answered that question. Okay, so what happens if there is an interrupt while we are between a system call in our kernel stack? Right, so it depends on your implementation. In RTX that you're implementing right now, or you will be implementing during ECE 350, we disable interrupts even when we're dealing with system calls. That's not necessarily true everywhere. So if you don't, then you could get interrupted while you're doing a system call, and that's fine, right? You use your kernel stack to continue dealing with the interrupt, and once you're done, you pop that, and you're left with the system call that you wanted to take care of, and you continue the system call, and then you eventually go back to the user program, right? So to just make things simple, in ECE 350 labs, we disable interrupts even when we're dealing with system calls, but that's not the case all the time. Okay, so this is an example. I'm going to just run through it really fast of x86 mode transfer. So there are a lot of components here. Let's talk about them one at a time. So this is basically the kernel code for dealing with interrupts. This is this kernel stack, which is empty at this point. This is the user stack, and this is the user code. So suppose that we're now inside this foo function. So the foo stack frame has been pushed on the user stack. And here in the middle, we're looking at processor registers. So the PC is pointing to somewhere in foo that we're executing. So PC is pointing to a code there. A stack pointer is pointing to the user stack, top of the user stack. And then the registers contain the registers that we are updating while running the user code. Let's say an interrupt happens. So once an interrupt happens, what will happen is immediately the mode. This is that atomic mode transfer that we were talking about. Atomically, at the same time, all these things that I'm going to talk about will happen in x86. This is different from what happens in ARM. I kind of touched upon what happens in ARM slightly during the tutorial. We'll probably have another tutorial to go over what happens if an interrupt or a system call happens in ARM later on. Especially for lab 2, you will need that. But here is x86. What happens is you atomically, I think I actually jumped over one slide, so I'll go back to it. But let's finish this one. What happens is, first of all, the mode changes from 0 to 1. So now we're in kernel mode. The second thing that happens is that the hardware pushes the old stack pointer and the old PC and some of the registers, in particular this E flags register. The operating system the hardware pushes all three of them to the kernel stack that it knew about previously. So you might actually ask, how does the hardware know where kernel stack is? And the answer is operating system, when it scheduled this user thread, went and set some register in the hardware and told hardware about this kernel stack and said, this is a kernel stack that you're going to use if you wanted, if a mode transfer happened. So operating system has previously told hardware where the stack lives. So this is done before we jump to the user process. Now we were running the user process and an interrupt happened or a system call happened. Hardware goes and uses that stack pointer that was provided to it to push PC, SP, and ELA, the E flags, to the stack, and optionally some error variables. Let's say if it was a system call or it was an interrupt with a particular number, hardware could also push those to the kernel stack. So that happens first. The mode transfer happens. Now hardware changes the stack pointer. Now the newest stack pointer will point to the beginning of to the top of the kernel stack, and PC will point to interrupt handler or system call handler or exception handler, whatever the mode transfer was triggered for. And all of this that I explained, all of it happens atomically. So all of them happen or none of it happens. So now we're at the beginning of interrupt handler. Usually you, at the beginning of your interrupt handler, you save the rest of the registers. So hardware saved for you the PC, hardware saved for you SP, hardware saved for you E flags, but the rest of the registers here are not saved. So usually we take a copy of them. The reason is inside your interrupt handler, you might actually start running functions, and those functions are going to use registers. So you're going to mess up with the user registers. To avoid that, you could save all the registers on the kernel stack. Now, in x86, you have limited number of registers, so it's easy to push them all. In systems like ARM, where you have a ton of registers, you could just push the registers that you know your interrupt handler might change. So you could have a convention that says interrupt handler can only change R0 to R5. But if you don't want to give yourself go through that headache, you could just save all registers. Now there's a trade-off. Saving all registers means going to memory more, because you're just basically, a stack is in memory, so you want to save each one of those registers, you have to go to memory. So if you have that convention that, okay, my interrupt handlers are going to at most touch R0 to R5, then you can just save R0 to R5. And that buys you time. That makes your interrupt handler overhead lower. Now in the labs, in ECE 350 labs, we took the easy way. We pushed everything. We didn't assume any convention. So when I talk about the SVC handler in our project, you will see that at the beginning of it, we're pushing all the registers. But it's not necessary. So if I'm repeating myself, if you know that your interrupt handlers are going to just touch few registers, you don't need to save them all. Now in x86, there's this instruction called push AD, and that instruction pushes all the registers to the stack. Now here is, I executed that instruction and all of my registers are now in the stack. You have to notice here that there are two SPs here. There is one SP that hardware pushed, and there is one SP here that is the result of executing this push AD. I usually ask students, are these two the same? But here in a online setting, it's not possible for you to answer that question. So I'm going to answer that question myself. They're not. So this SP, as you can see, is pointing to the user stack, right? This is the one that hardware pushed. This SP is the SP that I had when I executed this push AD. What was that? It was a stack that was pointing to this address. So basically, I'm going to push the address of here, the top of my stack here. So this is kind of like pointing to here. This guy is pointing to here. So they're different. Now, you might ask, OK, why am I just pushing this? Not really any reason. In fact, when you pop it, you throw it away. So the only reason that you're pushing it is because this push AD pushes everything, including SP. You're not going to use it. So when you do pop AD, a stack pointer is going to be popped and thrown away. OK. So let me go back to this slide that I kind of missed. This is more transfer steps in x86. Actually, now you could actually see it in just bullet points. x86 disables interrupts, saves PC, SP, and execution flag temporary somewhere. It switches to the kernel interrupt stack, and then pushes those three to the stack, and optionally saves an error code. So here are the steps that we talked about, and eventually it just jumps to the interrupt handler, and then so these are the things that the x86 hardware does for you. And now the operating system could then execute push AD, right? Push AD, and then whatever instruction after that to take care of that interrupt. Okay. Now, how do you do system call handling? There is a little bit of details here for you. I think the most important thing with interrupt handling, with system call handling, is the fact that with system calls, you usually get input from user program. So user program, for example, says, open this file. So it's giving you some input, some data, or it says, write this data to this file, right? So whenever we're interacting with the user, we should not trust the user. We have to check these arguments. Maybe it's passing us arguments that are bogus or garbage, and it's going to come and mess up the kernel code. So the first step. So with that introduction, let's go through these steps. The first step is like interrupt handling. You just go through your interrupt vector table to find your interrupt handler. So this is done by the hardware. We now are running. Oh, actually, never mind. I'm sorry. So this is actually different than what I said. So this is inside the interrupt handler. This hardware has jumped to interrupt handler. I'm actually doing this. We're implementing interrupt handler. Sorry. God damn it. We're implementing system call handler. Now, as I mentioned in x86, there is only one system call handler entity or entry in your interrupt vector table. So no matter what system call is, we're going to execute the same code. So this code is going to then jump to different system calls, right? Based on the input that is provided to it. So if you wanted to do open, it's going to go and call open. If you were running read, is going to go and execute read. So inside this system call handler, you're going to decide what system call it was that the user wanted to do. Was it reading a file? Was it writing to the file? Was it opening a file? Was it opening a socket? What was it that the user wanted? So you do that. Now, for your arguments, you have to find them. Potentially they're in user stack, or they might be in registers. If it is just a single number, maybe it's in a register. If it is, writing file, the writing data to a file, it's on the stack, the user stack. So you locate them because you have the hardware has kind of given you the stack pointer. If you remember, hardware pushes the stack pointer of user to kernel, so you have access to that. So you can locate where the arguments are. You first copy them to your own stack, and then you validate them. So this order is very important. You don't validate and then copy. You first copy and then validate. The reason is, if you validate, let's say if you have a multiprocessor and one thread calls a system call, the other threads are still running and they actually still have access to the stack of the thread that got interrupted. So if you validate the arguments on user stack and then copy, from when you validated until you copied, there is a chance that other threads go and mess it up. So you need to validate again once it's on your stack. The moment it's on kernel stack, we're kind of trusting that nothing can happen, right? The users at least cannot mess it up anymore. So now it's safe to check. You can check it, you validate it, and then you call to your interrupt handler. And once you have the result back, you just copy the result back to the memory of the user. I got a question. So there are no interrupt vector table in x86. What? How did you get that? There are no interrupt vector table? No, there are. I don't know how you got that idea. So, I mean, go back to this slide. We were talking about x86. Look, this was, we're talking about interrupt vector table in x86. Sorry, I don't exactly know how you got that idea. So maybe clarify your question. Okay. Now, generally speaking, handling system calls is time-consuming and heavy. So this shows you, this graph shows you, I think the ones that we're interested in are this one, a function call, a normal function call. The blue bars are the overhead of a normal function call, and these green ones are the overhead of system calls. And as you can see, they're orders of magnitude different. So system call handling is much more expensive than a usual function call, because of all the steps that are involved in making a copy of the context of the thread that got interrupted, checking the inputs, and then handling that in kernel mode, and then coming back from kernel mode to user mode. So all of these are very heavy and time consuming. Now, I think this is a good place to talk about monolithic kernels and micro-kernels you might have heard. So far what we talked about was a monolithic kernel, where we're talking about this part of this figure, where you have your application living in the user space, and everything with regard to operating system is executing in kernel mode. So whenever you want to run anything that is related to operating system, you run them in kernel mode. Now, this is monolithic kernel. This is usually what we have. The idea in micro-kernel is that to keep the kernel simple and small, and the intuition behind making that option is the smaller the kernel code is, the safer the system is because there are less bugs. The more code I'm running in kernel mode, the higher chances are that there is a bug and that bug messes up my entire system. So the idea is to just keep the bare minimum in kernel code, like basic inter-process communication, virtual memory handling, and scheduling. So bare minimum inside kernel, and do the rest of it in user mode. So don't switch modes, for example, to do to run device drivers or to do different things, right? Excuse me. Now, this is appealing, and it kind of was a hot topic in decades ago. But people soon realized that this is, although safer and more reliable, it comes with a performance cost. And the reason is this requires a lot of inter-process communication. The other thing is that it requires a lot of mode transfers. So your application is going to go to kernel and then come back to one of these and then go back to kernel and then go back to application and then go back again to kernel and go to one of these and then go back to kernel and go back to application. So a lot of mode transfers for a simple thing. Whereas in the monolithic one, you do one mode transfer and you stay in kernel mode. If you want to go through different components, you don't need to do any mode transfer. And once the result is ready, you transfer back to the application. So here you have two mode transfers. Here you might have a lot of inter-process communication. And for each one of those inter-process communications, you need a mode transfer. You need to go to kernel to then go to another process. So you end up having a lot of mode transfers, and that costs you performance. So I think there is also this hybrid model where you still keep the kernel bare minimum, but you probably want to do your drivers inside kernel and some of the other responsibilities of operating system running in the user mode. Now, as you can see in this slide, the idea of microkernels quickly became unpopular because of the performance cost of it. But it did have impact on operating system design. So some kernels, adopted this hybrid mode, and some others kind of, got some ideas, when it comes to keeping the kernel simple and small. The origin of this idea from microkernels had some impact in today's monolithic kernels. So for what's worth. Okay, so at the end of the switch, I know I'm going to finish with this slide. So after we transfer to kernel, from user to kernel, and we're done with the kernel functions, we want to go back to the user. So this is another mode transfer from kernel to user. Instances of this are when, let's say, you're returning from an interrupt handler or a system call handler. Or another example is when you create a new thread. So you usually, or a new process, you go from kernel to that newly created thread or process. And another example is context switching, right? When you context switch, you go from user to kernel, then you switch the context, and then you go from kernel to back to user. And finally, there is the idea of signals. So if you remember from ECE 252, we had this signal delivery. So let's say a segmentation fault happens or somebody sends you a signal. Operating system is involved. And then operating system switches to user mode to run the signal handler. So that's another example of going from kernel to user mode. OK, so I was hoping that I can finish this, but unfortunately I couldn't. OK, stop that. Get out. Let me see how much left. OK, I mean, we're good shape. So I think I can discard. I think I can just spend 5-10 minutes next lecture to finish this one up, and hopefully on Thursday we'll start talking about implementing multi-threaded kernels. So thank you for those of you who attended the lecture and asked questions, and thank you for those of you who are watching the lectures online. We'll talk to you guys on Thursday. Take care, be safe, and bye-bye.